Okay, so the first thing I want to do here is just kind of go over the equation sheet. The equation sheet you'll be given is going to be very, very similar to this. And what you need to understand is, what am I seeing? Okay, we have talked about so far, we have talked about normal, okay, and we've talked about shear. So when I'm looking at normal, I have to understand it's a specimen that's being pulled in tension or pushed in compression. We have that internal normal force. It is perpendicular to my cross section. And so when I pull on this, I'm going to have expansion or a contraction. So we could show that we have an original length. When we pull on it, okay, we end up with a delta, and our length final is length initial plus delta. We could also get shorter. We could also be shorter and have length final is length initial minus delta, okay? So when I look at this force on the cross section, I understand that I have a normal stress of normal, the internal normal, over that cross section. Okay? And there is a relationship between that stress and the deformation. Okay? So when I look at this, I have to recognize this is just that normal stress that occurs as I am pulling on or pushing on a cross section. This is the cross section, and it's the original that I have before we start pushing and pulling. This is that internal normal force. So when I cut a section, you know, I could have normal shear, bending moment, and torque. We haven't talked about any of those right now. We're looking at purely, this is from an axial, if you will. Okay. This is shear. Shear is, okay, it's a parallel force that is acting on the cross section. Okay, so this is from that parallel loading where we have that triangular deformation. So we have shear. And that is going to be that shear force that's acting on that cross section. And we end up then with a distortion. We have shear strain. Okay, so this is the shear force. This is the area, the parallel area that it's acting on. Okay, this strain goes with that normal. This is that change in length, okay, delta. This is delta. This is length final minus length initial over length. And this is the relationship between stress and strain when I am looking at the axial loading, okay? I also have Poisson's ratio, which is the ratio we can look at when we have this longitudinal and lateral strain. So longitudinal is through the axis that we're looking at. It's going to be the strain that comes from that change in length. Lateral is going to be that cross section. Okay, it has the negative because as we get longer, this gets smaller, so the strain will be negative. So we have a negative here so that Poisson's ratio is always a positive value. Okay, this is the relationship between shear. It's our shear stress and our shear strain. And if maybe we're given G and E, or we have the ability to find these, we can always find Poisson's ratio. So this relates everything, okay? This is our shear strain. Remember, we start at 90 degrees. That's pi over 2 minus. That's the internal theta right there, so that we can get the shear strain. This is law of cosines. And so if you have a bar that's maybe come down, and you know, it's going to displace down. If you had a cable that was attached, that cable is now coming here. You might need to use law of cosines in order to find the angle of rotation there. Delta. If we have a cross section which has a constant force and a constant cross-sectional area, then we don't have to integrate. We can just use that delta is PL over AE. However, if we have cross sections or loads which vary, we have to do integration. This is our, do you guys remember what that is? This is the area. This is a strain energy under the elastic region. It's the resilience, the modulus of resilience. How resilient are we? So when we look at a stress strain curve, it is this area. I just look at it as 1/2 base times height. It works out the same way. Okay. Now, when we're looking at material properties, the thing we have to keep in mind is look at all that stuff. Look at all of it. I have to know what goes with what. So this is normal. This is with normal. We haven't gotten to temperature change, so just ignore it. Don't throw that on your page. Okay, this is normal. These are normal. This is an E. This is normal and normal. Now, if we want to look at shear, shear is going to be the taus and g's. That's how our shear stress is related. And if we can't remember what goes with what, go back up here to your equation. I see a shear stress and I see a g. I see a normal stress and I see an E. And that way you can keep up with what goes with what in case you forget and you're panicky on a test. Just go back and look at your equations. So make sure that you understand the difference between normal and shear, and you understand which equations are going to go with which application.